it will not be symmetric.
If it's not FTDD, it's FTD, it's not symmetric.
But yeah, FTD is not symmetric. That's the main things, but probably.
Yeah, you don't need phase, you just need strength.
Yeah, so it's just pretty much.
It's very simple.
It may not be completely symmetric at the endpoints because of local fading. You're going to see a difference, some different geometry in general. Sometimes not really completely symmetric.
It's not completely symmetric because the base is not going to be symmetric, but the strengths will be roughly symmetric.
Exactly.
And what we need will be from the strengths.
And you just need the RSSI.
That's what you need in this history, which is single power.
Right.
Yeah. But so anyway, this is like a broad proposal, so I'd like to cover those issues as well. So I put that in the last of my talk. So I will first look at, so because these are lots of issues, and it's good to focus on small things. So I use a divider concept. So I look into so I look into the forest. And first focus on the coding scheme and the cooperative strategies, which is the physical layer issues. And also I want to focus on a small subsystem where I have only two transmitters and two receivers. Okay, so I could focus on this small subsystem, and I will abstract this engineering problem into an information theoretic problem. So the model I look at is called the Gaussian inference channel, where I have two transmitters, I have two receivers, and the channel gains, they are complex numbers. And the noise are circular symmetric competitive by Gaussian processes, and they are independent. And I assume that all the nodes know the whole channel, and the channel is static. So there's no variation in this model. All the numbers, all the channels are fixed numbers, fixed complex numbers. And in this scenario, each transmitter wants to convey a message to its own receiver. Okay, and the receiver is not interested in getting the other guy's message. And I'm going to summarize the channel parameters as follows. So SNR1, INR1 denotes the interference to noise ratio, and the SNR1, INR1 denotes the signal to noise ratio, and the interference to noise ratio at receiver 1. And similar things can be defined at receiver 2 as well. So here the index 1 and 2 are defined with respect to the receivers. And I'm going to assume that all the nodes on the whole channel, and I model the cooperation among these receivers by these two links, which are orthogonal to each other. So these two links, they are orthogonal to each other, and they are orthogonal to the interference channel, which is the wireless channel. So they're orthogonal to the these wireless links, and they are of finite capacity C21 and C12 respectively. So they are of finite capacity. I can do the same modeling for transmitter operation as well. Okay, so this is the model I want to study, and I want to find out the capacity for this channel. I want to study these channels to answer the question that how much interference can limited amount of cooperation be, and some related works. So the capacity region for these Gaussian interference channel without cooperation, they are even open. So they are only known for some special cases, for example in the strong interference regime. And recently the capacity region is characterized to within 1 bit, regardless of the channel parameters. So we have a approximate capacity region characterization. So I can have a 1 bit guarantee to the optimality. And the Gaussian interference channel with in-band source destination cooperation. In-band means that the cooperation is happening in the same band as the transmissions among the transmitters and receivers. This is a more yeah. So the cooperation is also interfering with the signals itself. So this is a more appropriate model for wireless IHWs, for example. And some work has been done, and recently some capacity of this channel has been characterized within constant move bits. So the argument that so this kind of characterization of capacity region to within a constant number of bits is important in terms of high SNR performance, because this gap between the achievable rates and outer bounds, they are not scaling with the SNRs. So as you drive the SNR goes to infinity, these gaps becomes vanishingly small. And
Relatively small.
yeah, relatively small. So it's kind of a characterization of the capacity in highest energy. So these guys have the characterization of this sum capacity within 18 bits and 40 bits. That's kind of huge. It's not very practical. Not of practical interest because they're huge. So our work is focusing on Gaussian differential with orthogonal cooperation. Like I said, it's a more proper scenario for more appropriate model for serial networks with backhaul operations, because backhaul is typically orthogonal to the wireless transmission. And we characterize the capacity region of this channel within 2 bits for receiver cooperation. So I want to, before I go into the detail, I want to describe the qualitative nature of the gain from receiver cooperation. So I will use a symmetric example, and this example is symmetric because SNRs and INRs and the cooperation rates, they are symmetric. And in this example, the SNR is 20 dB, INR is 15 dB, and I'm plotting the user data rate versus the cooperation rate. So the cooperation rate is C superscript D on the graph, on the diagram. And the blue curve is, and the green curve is the theoretic upper bound that I derive, and the black curve is the actual rate that I derive. And from this curve, you can identify 2 regions. One is the linear region, and the other one is the saturation region. The yellow one is the linear region, where the cooperation gain is economic, in the sense that it grows almost linearly as you increase the cooperation rate. And in this regime, the gain is a degrees of freedom gain. And the bottleneck in this regime is the cooperation limits. So I'm going to call this regime cooperation limited. On the other hand, in the saturation region, the gain from cooperation is very expensive in the sense that you get at most 1 bit of power gain as you increase infinite amount of cooperation into the system. Okay, so the bottleneck in this regime is the MIMO system over there. So we're going to call this regime MIMO limited. And through all this work, we're going to focus on the cooperation limited regime because the gain is more economic and it's a more interesting scenario for our setup because we want to study the effect of limited cooperation. So now I want to describe the gain from receiver cooperation in a quantitative way. And to better convey the key ideas, I'm going to use the symmetric example because now I have fewer parameters. So I can simplify the notations. Okay, so I'm going to use this measure, which is called generalized degrees of freedom, which is proposed in the study of Gaussian interference channels without cooperation. So I want to study the performance in interference limited regime. And it turns out that this number is a good measure